So if you're buying products today, the next generation of these are designed to be backwards compatible. When we start looking at water systems and the size of some of those networks, it's a lot of times there's long lead times in terms of from when we start talking about a project, we put it in, and then if you need to make some adjustments or add some additions, we want to make sure that there's a pathway forward that's very scalable and it's very compatible. Also, what that did, and especially this last year, is it allows us to have a much tighter control of that supply chain. So we build in smaller batches just more frequently, so we can react very quickly. And in kind of the very odd thing of today's world is actually all of our products are in stock. We're out based in Washington State, and then everything is actually made here in the U.S. We've got board houses in Washington as well as in California and Texas. And kind of what we do is we really have a complete comprehensive portfolio. So we have 8 different models plus a spectrum analyzer, and we cover both the FCC licensed frequencies, which are your 150 to 174 megahertz, your 270 to 220, and your 450 to 470. And these have been really kind of the bread and butter, kind of the really the baseline for a lot of you that have been in the water wastewater business for quite a while. This is really what everybody cut their teeth on. Then we also do the license-free frequencies. These are your 900 megahertz, 2.4, and the 5.8 gigahertz. And these are quickly overcoming the license frequencies. And we'll kind of get into that during this presentation as the why and what we need to consider with that is really kind of the meat of what we're going to talk about today. Today, we've got a little over 45,000 radios out worldwide. Predominantly, we're in the Americas, both North America as well as Latin America, and we do have a little bit over into Europe and the Middle East and in some of that area. And you kind of see down there what we've got kind of a different product families that we can go forward with. So as we kind of wade into what we're going to talk about today, we're really going to kind of break this into kind of the industrial communications itself and this what we call the digital transformation. Then we're going to look at some of the wireless modernization strategies, and then what goes into really designing today's wireless network. What do we need to consider? How do we make this actually function and get that data? Because that's really at the end of the day is what you're looking for or your customer is looking for is that data to be reliable and always there, very persistent. So we kind of look at where we're involved very heavily is in of course, water, wastewater, oil and gas, mining, material handling, power and energy, agriculture, kind of the all-encompassing infrastructure. And then we do a lot of factory floor and AGV. Now, water, wastewater is probably makes up about 60% of our business. So it's very close to the heart and really kind of what's driving today's discussion. But what we're seeing is across all these industries, and particular in water wastewater, is kind of this now move into the digital transformation. And what we're seeing, you can kind of go here, is we're really moving from kind of these old type of communications, and we're really now kind of into this what we call Industry 4.0. Now, there's really kind of a couple interesting things when you really break this down, because what we're doing is we're migrating from a serial-based communication scheme, which was really device level. It was PLCs talking to PLCs. Now we're moving into an Ethernet-based, and so not only are we evolving the data itself, how it's structured, but the biggest thing is now the entire kind of idea of this is we're now moving into a networked model or a connected model. So we're moving from device level communications. Now we want to have basically everything within that same connected model. So when we look at what that connected model really is comprised of, is really we've got the things. These are our devices. So you kind of want to think this is our Rockwell devices, the PLCs, things out in that field. And ultimately we need some connectivity, which is that network and the gateway. The data itself, and where is that going to be stored? And then ultimately, the only reason why that the data is going to be of any value is we've really got to be able to take and do some analytics. This is how, whether it's machine learning, we just want visuals, we need to be able to take and process that data and make it actionable data. Now, when we start really kind of drilling down into this a little bit more, when we start looking at these 4 pillars, and well, when we get into water, wastewater, it's a little bit different animal that we have to contend with. So some of the big challenges in water wastewater, when we start talking about this connected enterprise or digital transformation, is there are challenges that are different from than say a factory floor. We're typically looking at very long distances. These can be citywide, they can be countywide, they can be multi-countywide, especially down in the Florida region. We're stretching across large areas that we need to encompass. A lot of times we're trying to just get across waterways. We're trying to get across roadways. We're now bringing in mobile applications. Those can be, maintenance vehicles that are basically now going through the city that they want to have kind of a complete coverage and network connectivity within those vehicles. So really kind of what we're looking at is everything is really based with remote assets. Okay, this is really kind of why, we're here talking about this. Wireless communications is really what brings or solves all of these problems. So when we start looking at that connected water wastewater network, we really need to have kind of these 7 things or these must-haves. It's got to be reliable. It's got to be persistent in terms of that data acquisition. It's got to be there. We need to have edge-to-edge cybersecurity. That's a huge one right now. Need to be able to do both layer 2 and layer 3 connection types on your network side. That data itself, it's got to be able to either be on premise, it can be in the cloud, or a lot of places you actually have both. It needs to be scalable, very cost effective, and future proof. And then, it used to be that we had a very separated or siloed IT and OT. Well, that's very much blended now or blurring. And so it needs to be frictionless. It needs to be something that both sides are now working together on. So when we start kind of looking into this bigger distances that we're contending within the water wastewater, well, in order to achieve these pillars and get these different must-haves, that's a big jump, and so what we're seeing now is that a lot of times it's going to take modernizing a current network, or how are we going to modernize the current wireless network in order to pull this off. So when we start really looking at this a little bit deeper, is when we start talking about modernizing water and wastewater wireless networks, or putting in let's call it a greenfield application or a new system, we really have to kind of break this apart into 3 pieces. We want to look at the what of it. What are you actually doing? Is this a serial network still that's going to be migrating to Ethernet? Is it something that's going to be changing in the migration all at once? Other times it's like we need to increase reliability. We need better cybersecurity. Do we need to consider roaming or mobile applications out there? Like I say, those vehicles. Now all of a sudden we've got, the IoT or IIoT, if you want to look at it that way, where we've got mobile workers out there. We've got thin clients. Do we need Wi-Fi at these different areas? And then honestly, most of the networks now, there is no such thing as simply a wireless network or a wired network. We're dealing with a combination of these different technologies to give us these hybrid networks. Kind of the application demands or the what of the application. Then we need to consider kind of the where that we're talking about, the physical environment, and that's going to be things such as distance. But also what we're looking at is going to be terrain. It's very different out here in Washington State as it is for our friends down in Florida. Then we also look at the environment, and that's really kind of 2 different things. It's the RF environment as well as the physical environment. Once we kind of consider both of those and look at how those impact each other and which problems we need to solve, that's really going to drive us into kind of the how, or which frequency are we looking at, what kind of bandwidth do we need? Because really what we're looking at is what's the appropriate technology? How do I actually do that? So kind of how we've broken this down is we're going to take each of these kind of piece by piece. So when we start looking at especially modernizing, the water wastewater wireless network side, we're going to really look at kind of the what of this. So really the first thing, and probably the biggest driver, is there's this now change or this migration going from that, let's call it the DF1 systems into an Ethernet IP, or just the Ethernet itself is really what's driving a lot of this change. So when we start looking at Ethernet in particular, really where we need to start is kind of at the basics of it. Is so when we look at basically this the Ethernet stack, right? So we kind of have to look at how this is now built. So no matter whether or not we're talking about a wireless system, a copper system, a fiber system, cellular, we all live basically just down here at the physical and the link layer. And so we're doing the same thing. So typically if you can do it across, let's call it a piece of Cat5 cable, we can do it across a wireless network. And so this is really where we live. We don't, most of the protocol specifics is handled well above us, but there are some considerations if you're moving into an Ethernet or a modern Ethernet network, but we're applying that into the wireless world. So really, probably the biggest driver of these considerations is going to be speed and data rate. Okay, when you look at what the demands were for DF1 versus what they are for Ethernet IP, it's night and day difference. So when you look at those legacy networks, and these are still networks that are very much in place today, these are typically those legacy FCC licensed frequencies that we talked about before. This is your 150 to 174, your 217 to 220, your 450 to 470. These are incredibly robust wireless networks, but the big killer to them is that they're very, very narrowband channels, which means you get very slow data rates. So we start talking about data rate, we're talking in terms of kilobits, not in terms of megabits. And so by today's standards, you're typically at about 9,600 to 12.5 kilobytes per second. So we're kind of moving at the speed of a glacier there. So it can be done, but we've got to really look at that. Now, this is why we're seeing a lot more of the unlicensed or license-free frequencies now being brought into those equations and replacing out those legacy bands, because now all of a sudden we can get up to, say, 300 megabits per second of RF data rate. Now, we're going to get into a little bit in terms of some of the limitations of those, but the other one is because they are license-free, one big thing is that is open to others. So you're going to be sharing these networks with other users. And so it's something to be considerate of when we're moving into these wireless Ethernet networks. Okay. The other big one is link latency. So again, we look at those older FCC licensed networks. Pretty typical. It was, say, if you're just to think of this as running a ping or how long is it going to take to get there, about 50 to 100 milliseconds. Okay, when we get now into these license-free frequencies, in order to bring the Ethernet world in, now all of a sudden we can get into that 5 to 20 milliseconds. So why I bring this up is as if we're moving into that Ethernet world, is we've got to be, at least aware of what's going on, and we may need to be able to adjust those RPI values out within your controllers for what's available. It's something that this is how much pipeline you're going to get. We've got to adjust that system to be able to operate within that. The network architecture is another one that's changing, and that can be, do we have layer 2 versus layer 3? We've got to understand the network traffic. We may want to, basically isolate that network so we don't have basically your entire citywide network also going out over the Ethernet side of things on the wireless side. We want to leave that pipeline open for what we need, so we can go into a routed system. You can basically, are you going to be using this with VLANs and then basically trunking across this? This is another, I guess, very current and popular method of doing this. And then also if we need to prioritize that data or QoS, that can actually be configured within the switches. Say, okay, I want my SCADA data to have top priority, then video, and so forth. Those are other considerations we need to look at, as well as those smart port roles on your Stratix switches. It is choosing the correct one for a wireless network. Okay. Then when we start getting in even a little deeper into it, or a little bit further up that network stack, is the protocol requirements and the expectations of it. Are we setting this up for implicit messaging versus explicit messaging? Typically in a wireless system, explicit messaging is preferred just because it has a little bit better in terms of retries and guarantees of that data being there. Kind of also, are we doing UDP versus TCP? There's basically trade-offs for each of those. Biggest one you want to consider is that any wireless system, kind of a modern wireless system, think of that as a half duplex length. We're either transmitting or receiving And so we're not necessarily running parallel. It is basically as a half duplex if you want to consider it that way. And so you want to think of if there is a missed packet, what happens, and so it's going to be programming in retries or what happens that way. So in the Esteem world, what this is this is our Horizon series, and this isn't going to be a big sales pitch, but I just want to make you aware of, from Esteem, we actually have a family of radios called our Horizon, and that's available in 900 megahertz, 2.4 gigahertz, and 5.8 gigahertz. Now, the 900 is very interesting because we can get some of these technologies that have only been reserved for the higher frequencies, but now we can run it down in that 900 megahertz, which is going to offer a little better range to it, as well as a much higher level of security because it's not part of the open Wi-Fi system. But what all these share is that we can now get into industrial mesh, and this is what we're going to have for the self-healing networks. This is how we can make a redundant pathways. It can be very scalable this way. We're not limited to kind of that master-client relationship. Everybody would have master capabilities. Also, as we migrate, is now everything is up to an AES 256 encrypted connections, and each one of those connections can be handled on a separate encryption key. Supports layer 2 as well as layer 3 connectivity. It's a single device, but we have multiple modes for this. So we can be fixed location, we can be just kind of a flat network, or we can get into a routed network, or the same unit can be put into a mobile mode of operation, which allows it to roam throughout a city, kind of handshaking between your base stations or the towers and the pump sites and everything else. Very simple configuration. We've got graphical, kind of a drag and drop based utilities for configuring these, so it's very, very simple. And so they all have their own web page, but it really depends upon what your comfort level is in terms of the configuration. We want this to be as easy as possible. Then they're also pole mountable, and why we do that is when we get into the high frequencies, there's much greater loss, signal loss or attenuation within those cables at the higher frequencies. So when we built this radio, we actually built this, and when it's deployed, it's a NEMA 4 box, but we can mount it up next to the antenna and eliminate that feed line so we can get better range out of it and we can get better performance out of that as well. It doesn't have to be mounted that way, but it is kind of why we built it, to be able to do that. And then kind of the last piece is in the 2.4 gigahertz and the 5.8 gigahertz radios, they also have Wi-Fi capability. So it can double as not only that kind of your backhaul or that mesh system, but it can also be an access point for those mobile workers or your thin clients. Okay. So as we kind of progress down this and we start looking, another big reason is we want to have better reliability. The older radio systems, you had a dedicated path. This is going to basically go from X through a repeater out to Y. Well, what we want to build is the ability to mesh or have a self-healing network. This is an incredibly powerful tool to be able to do. So when we start kind of looking into this mesh technology, we kind of want to stop and say, okay, what's mesh? There's a lot of different variations and there's a lot of different interpretations. So mesh itself, where it came from, is ultimately kind of a buzzword that's been within the wireless industry. Where it came from is back in the Zigbee days of part of the, if you care, the IEEE 802.15.4. What it was designed for is essentially these devices, these little Zigbee devices were very low powered, and so they would kind of daisy chain in order to basically cross a larger gap of an area in order to kind of overcome distance of those low power and relay that information further along. Well, today, what we're talking about is in modern language on this industrial mesh, it's kind of a whole different purpose. So what it is, it's done to create these automatic self-healing redundant backup communication paths. We want to basically say this is a primary route. If that were to happen to fail, I want to move over to a backup route. This all happens in the background. There's really nothing that you have to do. And so then we also want it to be able to recover from that. Also, this can be used just strictly for a canopy for a mesh system or for a Wi-Fi system. And so one of the other things that we do is that each one of these routes is completely configured and controlled and prioritized by you or the integrator as the user. We don't necessarily want it to be strictly a algorithm that figures this out, because what we use is simple spanning tree protocol, and we support both spanning tree, rapid spanning tree, and multi-spanning tree. But when we get into the wireless world, sometimes that shortest path isn't always the best path. And so we enable you to be able to control that and prioritize those routes. And this will make sense in a couple slides, because I will actually show you what this looks like in motion. What we've also added into this is now we can control those routes not only by whether those connections are there, but we can actually now dynamically control this based upon signal strength. So if the signal is dropping down too low, now we can force that to move over to the backup path as well. So this is done for really a couple purposes. Number one is to maintain a higher data rate if you're doing something like a very high stream video. Also, what it is we can now do almost a mobile mesh to where we can use other vehicles to act as relays to other vehicles. Okay, the whole idea of this is really nothing more than to assure data reliability between your devices. We want to make sure that that data, when you need it and when you're requesting it, is going to get there. So when we kind of take a look at this in action, what you can see here is we've got the black lines would be our primary routes, and then the red dashed lines would be redundant backup paths for our network. And so what the idea is so if we're functioning through this, is basically we're operating on a primary path. If we seem to have a problem, say we shut down the power at a water tank because they're painting that, what we want is that network to basically reconfigure itself and reroute or heal. A lot of times that's self-healing. We can do the same things like, okay, we've also lost this, so now we're going to, again, readjust. And this is going to happen again all in the background, and this is being monitored about 10 times per second. Every 100 millisecond is when these beacons are going out. Now that's something that can be configured if you want to go faster, but that's really kind of a good setting that we're using. And this just can really any different way that we want to program these radios to overcome if there's a problem. Okay. Now the big key also is now all of a sudden if we get the power back to, let's say that tower or the water tank, is we want to make sure that it has the ability to roll back to its primary routes that you've already established. And again, this is something that's automatic. It's going to happen in the background to give us that reliability. As we kind of looked into our what a little further, the other big one that we're looking at is cybersecurity. The older networks, whether they had subpar, encryption or no encryption at all. It used to be kind of the security by obscurity was kind of how things rolled out a long time ago. Well, that's no longer the case. It's not something that's feasible to be able to have a network that way anymore. So when we start looking at on a modern wireless network, really, and I'm not going to get into a full blown because we could talk all day on security and different methods, but really there's really two things that pop up when we talk about modernizing that. Is kind of two things. One is that data security or the encryption of it, and then we're looking at network access, and those are really the kind of the 2 points we're going to talk about here. Is these are the two big drivers on modernizing or putting these things in. And we start looking at wireless encryption. Today's modern system is something that we use AES or Advanced Encryption Standard for that data now. Okay, and so kind of the norm, I guess, or standard is 128-bit. You can also do 256. There's some in-betweens within that as well. Everything we do now is able to be up to AES 256 encrypted connections. You also have basically the WPA2. You may have heard of this, and basically this is kind of your Wi-Fi encryption methods, and it really defines the process for that connection. Okay, so there's different ways. So we have the encryption itself. Then how do we actually encrypt that? Well, there's really two sides of this. We can do a pre-shared key, which is kind of that passphrase, very similar to what you use at your home. I put in Chambers as my passphrase, and that's going to generate a key, and we only need that. Well, as we get into these networks, if that's not sufficient, what we can also go in is you're going to have what they call an enterprise mode. And really what that is, it's an authentication server in which there can be certificates. A lot of people use a Radius server in order to start that communication. So there's other credentials to prove that you're allowed to be on that network. Either is acceptable. The enterprise is probably something that is a higher level of security, but it's not as seen as frequently, especially within the water wastewater side of things. Most of those are still using on a pre-shared key. Again, it's choosing the best method for what we have available. Then you also have kind of the older legacy encryption out there, which was your WPA, or if you've been in this even longer than that, the WEP encryption, which was really never designed to be high level encryption. It was more of a privacy type of a thing, something that it was a static key that could be pretty quickly deciphered. So that's why we've moved past that. But a lot of the older hardware isn't capable of anything beyond WEP. So it's another big driver for getting in this on the cybersecurity side of things. So when we look on this on the network access side of it, there's a few things that we can add into that with modern technology is an access control list. And this is basically as a MAC filter for clients. So we can basically allow or deny particular MAC addresses for different equipment. It's very simple. It's probably also the most difficult to break that way because you basically would have to know what that MAC address is. Now we can also turn the radios off so that they don't allow any Wi-Fi traffic, or it basically denies all MAC requests in there. You can actually allow all. We can go in and have particular MACs allowed. We can even have particular MACs denied. So if you have a disgruntled employee that had a phone, we can also make sure that they're no longer able to be on there. So basically, it's just a method of allowing and or denying particular Wi-Fi clients, and this is within that the 2.4 and the 5.8 gigahertz frequency bands. We can also, what you would do is we can now have the ability to disable the broadcast probes and hiding the SSID. So it essentially sets it so that that network isn't visible to somebody sitting out in the parking lot. By hiding that, so there's really two methods. There's kind of a passive mode where you're just listening, if you've seen kind of sitting in the hotel, or you go out and probe for them, so you can actually turn both of those off. And so what that would require is that you would need to know that SSID in order to join that network. Okay. Then also what is now being added in, and you'll find that within the latest variation of the firmware that we're doing, is we want to make sure that we also have what they call a protected management frame. That was kind of the last piece, is that management frame controlling on that access was unencrypted. Well, now that's changed, and so as we're moving forward, is not only are the radios compliant with that, but you need to make sure that your end devices, your laptops and things are set up to be able to do that. It's kind of that future proof for the next gen of wireless security. Okay, the other one is different frequency options. Okay, so we can go into a 900 megahertz, which is a non-Wi-Fi band, if we want to even further enhance that security, in addition to the 2.4 gigahertz and the 5.8. Now, what we can also do, even at those quote unquote Wi-Fi bands, is that we can now go in and you can select this for non-Wi-Fi channel bandwidth. So you can go into a 5 megahertz wide or a 10 megahertz wide channel that basically do the same thing. It disappears from that 802.11 Wi-Fi world. Different methods that we can actually do this. So when we kind of look at, beyond kind of the basics there, when we get into the advanced security so when we start talking about, Wi-Fi, what that's defining really is strictly an AP to a client. So it's basically is a gray area of how do we encrypt that between Esteem radios on this wireless mesh bridge. And so that's all completely proprietary. So the only thing is going to talk to, let's say, an Esteem radio is going to be another Esteem radio. So the interoperability disappears, but we increase that level of security. Okay, so we can support both bridge and AP simultaneously, and those are controlled independently. So that the encryption key for a bridge link can be different than what it is for an access point to a client link. Okay. We can also go into, we may want to have this into a router mode in which we have a different subnet. We can use static or DHCP addressing. Then we also go into a firewalled mode, or we call it a masquerade mode on there. You want to use the highest level of security, so we want to make sure that we can support AES 256 on these. I kind of mentioned at the beginning of this is that it is backwards compatible to previous generations of radios. And so that would be the limitation, is some of that older equipment didn't have that ability. So sometimes we'll have to adjust it to support that legacy encryption level, say like a WPA or an AES 128 only. And so downward compatibility is something to consider. Okay. As we kind of get into these others, when we start talking about mobility, is, today's mobile networks, the requirements that we have is ultimately, we've got to have higher speed to this, so we want to have 20 megabits or better, and for a mobile network. Seamless roaming, we want this to basically handshake, as your maintenance vehicles are driving through town. How do we actually handshake that as opposed to lose a connection, then gain a connection? We want it to work like your cell phone, or at least how your cell phone is supposed to work without dropping that communication link. So what we've done is basically that's controlled at the client level, and then you can actually base that upon signal levels or what your required data rate is going to be. And we also want to be very flexible in terms of that frequency. Again, if we're looking at these bigger networks, because they're shared frequencies, is we've got to make sure that we're avoiding interference. The IT, OT, sometimes they may have two different networks, so we've got to be able to be adjustable, and that could be a channel adjustability, or we could get into, a different frequency altogether. Say 2.4 for the IT guys, you could run 900 megahertz for kind of the OT side of things. Then also the license-free operation, as I said, is it's good because we don't have to license that, but you are going to have other users. There are some different international restrictions, which probably doesn't apply to here, but you get into some other countries and they will have a much lower output power that's available. And we'll get in a little bit more in terms of this when we get into the where and the considerations for which frequency should I use. And so that part is kind of coming up here as well. The other one that we're getting now is there's a lot of desire or need to get kind of the IIoT connectivity. And so depending upon your version of what IIoT is going to be, really what we're seeing this, and a lot of it is driven from the consumer market first, is that most of the IIoT is going to be Wi-Fi driven. Things like your cameras and sensors are all Wi-Fi compliant. Your thin clients, mobile workforce, this is kind of where we're looking at that first layer in there. And so what we're looking at is your Wi-Fi sensors, Wi-Fi cameras, location tracking. We've got to contend with thin clients, maintenance vehicles, maintenance personnel, without having to physically connect into this. They can do this a little bit more remotely. We even have people that are using for Wi-Fi calling on their cellular phones if they don't have cellular connectivity. This kind of all falls into that overarching IIoT side of things. And so when we look at that, what that requirement is we want to have that to be able to be both the mesh side of it as well as that Wi-Fi connectivity side of it in one single unit. It also, we want to have that to be able to be scalable. So we can do something like a twin bridge, and we can have kind of a dual SSID. We could have the process guys on one network, we could have video on another network, and have them completely isolated or air gapped, if you want to look at it that way, to enhance security. So we're going to have kind of that complete edge-to-edge connectivity from basically that your master location all the way down to down to that maintenance worker or that camera. Okay, so on the security side, we want to make sure that we've got the highest level of security. We want to make sure that we're using AES 128 or 256. We can filter this by the MACs, as we were talking about in the pre-shared key and the protected management frames. Again, we'll look at, if we're looking at this IoT or the Wi-Fi side of it, we've got two options. We can do 2.4 gigahertz and 5.8 gigahertz. Both of those have Wi-Fi bands within those. Okay, and then really kind of what we're seeing is when we start talking about hybrid networks, really what we have there is this is really all over our networks already. So we're looking at, we've got copper, networks that are doing the individual connectivity. We may have redundancy built into a fiber optic link to be able to have on our network, or that may be bridging out to particular locations, in order to connect our things back and make actionable data off of that. So we're already using, multiple mediums here. Now, when we get into this water wastewater side of things, this is where wireless makes sense, because now we're going to bring it in, and the data itself, that's kind of the beauty of once we went to Ethernet, is it doesn't care. It's going to flow like water based upon where it needs to go across multiple mediums. So we can have a fiber link, we can have copper links, we can have a wireless link. We may get into spots out there, say for a lift station, in which it's not even feasible to put, say, a traditional radio link out there. So we can bring in cellular and bring it into the network as well. So, the medium itself is no longer a hindrance. It's actually an incredible tool of how do I get connectivity to where I need it to get and use the best method for that. And all of them are going to blend, and they're going to be kind of a hybrid network. And that's really kind of the idea, is how do we integrate that into a complete edge-to-edge connectivity. Okay. So I don't know if there was any questions that popped up on that, or we'll keep kind of rolling through this. I know we've got some time constraints, so I don't want to get too hung up on things, because we still have kind of the where to go through here. And this is really, where the rubber meets the road is choosing correctly. So we really need to look at distance, terrain, and the environment, kind of that wireless landscape. So when we start looking at it, the first one we're going to look at is distance considerations. Okay, so distance, but basically how far between your locations do you need to communicate? Now, why I bring this up is because, as we talked about before, there's different frequency bands out there. So when you got into the FCC licensed frequencies, your 150, 450 range, these were very typical to be 10 to 20 to 30 mile links between these locations. They were much higher in power. And then when you get into essentially, how the electromagnetic waves at those different frequencies come about, we could go a lot further between locations. As we move into this license-free world, which is your 900 megahertz, 2.4, and the 5.8, now that typical range, we're going to shrink that down typically to about 3 to 7 miles from that 10 to 20 mile range. So we got to be thinking of this as we're going forward. Because when you look at it, that transmit power, with the licensed equipment, it really came down to what the FCC would license, but typically it was somewhere in that 5 to 25 watts of output power, versus the maximum the FCC allows now is 1 watt. That's a massive difference that we need to look at, because when we look at how much signal is received, what that is really a combination of how much power am I transmitting out of the radio, how much are we gaining by the antenna, then we have what they call a free space path loss, and I'll kind of bring into that, but that's basically how much do I lose going through the air, and then we have on the receive side, the antenna gain of that. Now, this free space path loss really comes down to the amount of signal as it propagates through space or an area. As it expands outward, we have reduction of power levels. One of the things is we deal with a lot of kind of this invisible world, so trying to add a little bit of visual to it, and so if you want to kind of look at this as if you take, a very kind of a heavy rubber band, right? We've got X amount of rubber that is made up of that rubber band. As we stretch that rubber band, we're going to have thinner, the tighter we stretch that, or the further out it goes. So as that intersects with that antenna, we're receiving less of the total amount of energy. Okay, so sometimes it's a little easier when I'm holding up a rubber band, but it kind of loses its value when we're going into a virtual world. But if you kind of think of that, if you put it between your fingers and you start stretching that out, just look at the amount of how much of that rubber would intersect as that gets thinner. So as well as the higher frequency, we have greater loss compared to the low frequencies. Okay, so why do we bring this up? Well, not only in terms of range, but as we kind of look before, in order to get into the modern Ethernet networks, requires more data rate, needs more throughput. So again, we're using those unlicensed frequencies. So when we look at those data rates, in order to achieve those data rates, it requires more signal. So back in the legacy narrowband networks, it's pretty common to have, say, a minus 100 dBm of signal gave us a fantastic connection. We're moving small amounts of data. We don't need real high data rates. As we get into this modern Ethernet side of things, now in order to get those high data rates, we need a tremendous amount of more signal, say like a minus 65 for the highest amount of data rate. Now, without getting, I guess, kind of radio dorking this too much, but to kind of give you an idea of scale on dB, it's a logarithmic number, and we can, and I won't bore you with the math, but if you come out of this with kind of your wireless 101 knowledge, is you want to remember the number 3. So every time we have a loss of 3 dB, we're cutting that power in half. Every time we gain 3 dB, we are now doubling the power. So you can see, minus 100 and minus 65 might not sound that much, but it is an incredible difference in terms of signal, because every 3D we're doubling it, or every 3 dB we're cutting it in half. Then another 3 dB we cut it in half again. Okay, so really kind of the key takeaway of this part of it is, don't assume that taking your older system out means that you're going to have connectivity with a newer system. If we're moving from, especially in the water wastewater, maybe a 450 megahertz network, I got these locations, my radio network worked fine, I'm going to just put in a 2.4 gigahertz. Don't assume that that's going to work, because we have much less power and we need much more data rate. So it doesn't really mean it's going to be a simple drop in. So we've got to do our homework on these to make sure. And it's very simple to do. And we're going to kind of look at what those steps are in order to make sure that that works, as well as something that from an engineering services side that we can not only help you with on a math model perspective, we can also come out and do a full-blown site survey in engineering services. And that's something we can come out of Washington State. As Claire mentioned, Jay is coming on board, so he can, especially down in the southeast there, he'll be able to come out and do that service for you as well. Okay, so when we start looking now at the other side of it, so okay, we got distance, how far am I going? Well, next we got to look at the terrain of it. And so again, data rate compounds this issue. We need to move into these modern Ethernet networks are going to demand more throughput, so we got to go to an unlicensed frequency. So when we start looking at how does that frequency behave in different terrains, probably a good way of looking at this is kind of this ladder. So down at those lower frequencies, down at that 150 megahertz, you can see is we could penetrate all kinds of line of sight obstruction. It was something that it was very difficult to make it not work. From an RF perspective, it's fantastic. From a data standpoint, is 9600 baud rate going to be enough? Okay, so as you can kind of see, the higher in frequency we go, the more dependent we are on unobstructed line of sight. 900 megahertz is a huge workhorse with industrial automation, because we can live with a little bit of line of sight obstruction, tolerates the most of the unlicensed bands, but it's not going to function quite as well as, say, 150 megahertz. But once we get up to, say, 5.8 gigahertz, we've got to have an unobstructed line of sight, or we're simply not going to be able to make a connection through that. So something to keep in mind is not only that distance, but what are you trying to go through? We may have to have increased antenna heights. Now, kind of further compounding this, and this is less of an issue, for our Florida friends, but as we get into California, we get into Washington, up into the Northeast, we're also now contending with you know, elevation differential or hills or, mountains. Those lower frequencies also had a kind of a ground crawl to it to where you could actually flow over a hill and get to an antenna. So not only could it go through things, as we could actually get some ground crawl to it. Well, that isn't going to be something that you can get away with when we go into these high frequencies. Again, it's very line of sight dependent. So it doesn't mean that your system isn't going to work. We just got to have to overcome those potential terrain challenges. So what that means is we may need to have repeaters. Now that's going to be a dedicated repeater. The other nice thing is, as these mesh networks, if you remember that diagram, any location can be a repeater for anybody else. We don't have dedicated master locations. We don't have dedicated remote locations and dedicated repeaters. Anybody can act as a repeater for anybody else while also acting as a remote or even that master location. Maybe we need to adjust and use 900 megahertz, or we can actually use multiple frequencies. There's a lot of networks that say we may have our backhaul running on 5.8 gigahertz, which has more robust speeds or data rates, and then use the 900 megahertz to get into some of those uglier terrains where we've got to park lift stations down in ravines and things of that nature. There may be times where we just simply can't do that with traditional radio. Let's bring cellular into it. That's something that we can also do, bring that right into that hybrid network and bring that location in. So again, it's kind of rethinking this is I don't have to go, number one, I'm going to a high frequency. What are our challenges? And I'm not locked into a single frequency. We can have multiple frequencies or multiple different ways of doing that. Okay. Then we look at the environment itself. And so there's really kind of two sides to the environment. So the first one we're going to look at is the RF environment. And kind of what we're looking at there is these networks that we're doing now for the modern Ethernet. These are the license-free frequencies. So you're going to have other users out there that you're having to live with. So now the good news is there's multiple channels within those frequencies so that we can try and get onto something that's isolated. Now, in order to do that, we can either play kind of a guessing game or we want to look at it with a spectrum analyzer. And so what you're seeing here is essentially just a snapshot in time, and people will call this a waterfall because this is moving. But if you want to look at this from kind of an eye standpoint, is what we have is if you see any of these little color blips out there, that's basically energy on that frequency. That's another user. That's somebody else that's actually out there. Because we're on a shared frequency, we're going to have to contend with this. So we can actually look at these and find an area in which that's going to be something that's going to be very, very open, because we're looking at not only how much signal is there, but also duty cycle. How often is that occupied? And so there's actually a tool, the spectrum analyzer, and it's something that we, when we come out and do, it's something that you can rent. It's something that you can purchase from us called an AirScope, that we can actually look at the different frequencies all in real time simultaneously and make an informed decision. I'm going to use 900 megahertz on channel 4, and this is why. Okay, we want to take that guesswork out of it. And so, where you're starting to see this is, kind of think of it as you've got neighborhoods, where a lot of this equipment is going, that you're having to now in a water system, we've got to now be in the middle of these neighborhoods. There's a lot of home Wi-Fi routers. You've got schools, that's all lit up for wireless, especially now after COVID, is there's so much more connectivity at these locations. You've got to we've got airports. Believe it or not, you've got fast food drive-throughs that are running on wireless. You've got handheld voice radios. Around ports and train yards, you've also got a lot of changing dynamics as depending upon what ships are coming into port or on those trains when that's going on. You've got wireless ISPs. Honestly, you also have to contend with your own interference or your own network. So, you may have, and I know I'm probably preaching to the choir, but there's a lot of places where the water and the wastewater guys, they don't play nice together. A lot of times they'll have their own network for the freshwater side and a different network on the wastewater side. So we want to make sure that we're we're basically have some channel management with that. Okay. Now, the flip side on the environment is the physical environment. Okay. So we'll just kind of throw this out there again. We're moving into this unlicensed world. Well, the higher frequencies are much greater impacted by things like rain, snow, fog, believe it or not, hurricanes, where you have all of the above of, you've got the rain as well as those winds blowing some of the antennas out of alignment. There's a lot of things that happen that we have to be cognizant of, especially within those unlicensed frequency bands. That we're also are we dealing with an indoor application or an outdoor application, or is it a combo? You're dealing with reflections and what it's bouncing off of. We don't want to mount antennas directly against walls or the outside of a tank. So you can actually look at it in terms of odd multiples of a quarter wavelength, but then when you also get in dual antennas, things of that nature. So when we're designing that network, we want to kind of realize that these are going to happen. It's going to rain, especially in Florida. You guys get some rain. In Washington, we get some rain. Warren in California, you're seeing some rain. And so what we want to make sure is that we're designing this system with what we call in the radio world fade margin, but think of it as we want to have an abundance or a little bit of extra signal. So if I lose some signal because we're in the middle of a snowstorm, I want to make sure that I build my system to have an abundance of signal so I can absorb that, or I can actually live with that. Okay. So as we kind of get through that, great. There's a whole lot of stuff I need to be aware of. How the heck do I choose which frequency is best for my application? What do I do? Well, that's a question we get. What's the best frequency? The answer is they're all fantastic. They all have their place and purpose, but we need to find the best one for your location and your application on there. So really, it's a pretty simple 3-step process. We look at this and say, okay, first what we're going to do is we're going to start off with an RF network design. And this is something, and we've designed a tool. It's just an Excel based. You can download it off our website. I'll get it to Claire so that you can actually, if you want to get it from her. But what this is basically a software feasibility study. And what we can look at, it says, okay, based upon this frequency with this antenna and this much feed line, if you're going to mount it traditionally, across this distance, how much signal can I anticipate? Let's look at the math side of it. And this is really done, it's a very conservative model, because one of the things with RF is there's a lot of marketing hype around some people's ranges that can be proven mathematically, but we want to give you a tool to be able to look at it. What's realistic? What can we anticipate this working? Because pie in the sky doesn't do anybody any good. We want to make sure that you're basing the system conservatively so that we know it's going to work. So in addition to what those signal levels are, most time what you as the end users or your end user customers are looking for is what kind of data rate can I achieve? And it's going to actually tell us what that is also. So what can we actually, can I make the link? And this is something that we can plot very simply on Google Earth. We can look at this, then we start diving into this a little bit deeper. If you want assistance with this, like I say, you can contact, Claire or Jay or myself, and we can assist you with that as well. Okay, once we get past that, then we get into the actual radio site survey, which is nothing more than just a physical on-site analysis. This is where you're going to evaluate software modeling results. Am I getting the amount of signal that I need? What we're learning here is things like antenna heights. As good as Google Earth is, there's some limitations. There are, it's hard to gauge, if that picture was taken 4 years ago. Are there buildings in the way now? Is there a new apartment complex that we need to contend with? Is there trees? How high do we need to be on this? The other one is okay, which frequency or channel within that do we need to look at? And so that can only be done on the ground with a spectrum analyzer. So we can see that. We can make some guesstimates, but we want to make sure and make sure that we take a sound approach to this. What we also look at is this is where we can determine maybe some alternate or redundant routes. If we find that there's a building now in the way, is looking around, say, can we use, City Hall to use as a repeater off of this? There's a lot of different tools there that we can help identify, and that can be identified during the radio site survey. Kind of the final step in this is actually the installation and the commissioning. This is when we're actually putting the equipment in per site survey, where we test that RF communications. We also realize, especially within water, wastewater, is that process from when we start talking about a network to where this is actually going live. This can be measured on calendars, not necessarily hours. So we may need to adjust channel. We need to look at, what's changed out there. So this is another very important part. And so the documentation at this also is critical of this is what it, the amount of signal I achieve when I'm putting this in. So if you've got to go back in and troubleshoot this, whether that's a month from now, 5 years from now, we know what kind of signal we had, what kind of data rate, what the path was, what kind of heights we had. So the documentation is very critical with this. And then we go live, then we actually turn it on and start pushing your data through it. Okay. So that kind of wraps up. I know I'm not up against the time here. And so, when you're ready to modernize your network, Rexel and Esteem can help. We've got the equipment. Like I say, everything is actually in stock. We've also got the engineering services. One of the things that we do that we can come out and assist you with, and this is something, is kind of doing these wireless network audits. A lot of times, like, I know I need to do something and I want to do it, but where do I start? And so we can come out and give an assessment or an audit of your current wireless network, what the needs are, what the shortcomings are, what do we need to do to bring that up to speed? Then we can come out and actually do these 3 different processes for you, or we can assist you with those. Okay. So with all of that talk and ideas and thoughts, I don't know if there's any questions that you have, or if Claire has seen any questions pop up. We can discuss those now. We also, this modernization that I was kind of talking about, we've actually got all that on our website that you see down that link at the bottom. If you've got any questions, you can email to me, you can call. The other one is we've got next week tech tour. There's actually 2 of them coming up. Hopefully I'm not stealing any of Claire's thunder here. Coming up, and so actually we're going to have the equipment there. Jay Chambers will be at both of these events, both for Tampa as well as Orlando, to be able to answer any questions. And
thank you very much for joining us today, Dan, as usual, as a guru for me with telemetry. So thank you very much. And I hope to see all of you from the Florida region at the tech tours. Otherwise, that's it. Have the rest of your afternoon and enjoy it. And call me, text me if you have any other questions that pop up after. Again, I'll be emailing or putting a link for all the presentations and recording, so you can download them at a later date.